Now we shall see how computers handle numbers and use logic gate networks to do arithmetic. We are all used to base 10 numbers, meaning that there are 10 digits from 0 to 9. The digits represent multiples of powers of 10, which are 1, 10, 100, 1000, and so on. Modern computers use base 2 numbers, with just 2 digits, 0 and 1. Binary digits are multiples of powers of 2, which are 1, 2, 4, 8, and so on. For example, in base 10, the number 953 is 9 times 100 plus 5 times 10 plus 3 times 1. In binary, the number 101 is 1 times 4 plus 0 times 2 plus 1 times 1, which is 5 in base 10. Any number in base 10 can be represented by a number in base 2 and vice versa. To represent the number 101, 3 electrical tracks in order would have their voltage on, off, on. Each of these tracks carries a binary digit or bit. With 3 electrical tracks, this is called a 3-bit number. There are similarly 4-bit numbers, 8-bit numbers, and so on. Of course, the 4-bit number 0101 is equivalent to the 3-bit number 101. Let's consider adding together a pair of 1-bit numbers A and B to get C. 0 plus 0 is 0. 0 plus 1 is 1. What happens when we try to add 1 plus 1 in binary? The same thing as happens when we add 5 plus 5 in regular base 10. There is no digit big enough, so we put a 0 in that column and carry the 1 to the next column. So to guarantee being able to store the result for any possible values of A and B, the result C must be a 2-bit number. The bit on the right is 1 when A or B is 1, but not both. This is the behavior of the XOR gate, if you recall Charlie from the last section. The bit on the left is 1 only if A and B are 1, ergo the AND gate. Therefore C is obtained by connecting A and B to gates like this. When adding numbers A and B larger than 1 bit, things get more complicated with 3 input gates because there is now a bit from A, a bit from B, and a carried bit. As I said in the previous section, NAND gates are universal, meaning that any required gate network can be implemented using enough of them. In base 10, multiplying by 10 is easy. Just add a 0 onto the end of your number. In base 2, the same is true for multiplying by 1 0 in binary or 2 in base 10. So multiplying by the numbers 10, 100, 1000 in binary just involves shifting each bit to the left and putting a 0 on the end, which is unimaginatively called a bit shift. What about multiplying by an arbitrary number, say for example 1 in binary? This is the same as multiplying by 1 0, multiplying by 1, and adding the two together. So binary multiplication of A by an arbitrary number B works as follows. Begin with 0. If the rightmost bit of B is 1, add A. Bit shift A once, and if the next bit of B is 1, add this to the total. Continue for every bit of B. Computers also rely on making comparisons of numbers, such as is A equal to B, is A greater than B, and so on. The computer might have the current time in seconds stored as a binary number A, updated every second, and the time to set off an alarm stored as B. The alarm would be made to go off when A is equal to B. To do this, the computer must check that every bit of the number A is the same as the corresponding bit of B. So the XOR gate returns 1 when an input is 1 and the other input is 0. In other words, when its inputs are different. The XNOR gate, which is the complement to the XOR, meaning it returns the opposite to the XOR, therefore returns a 1 when its inputs are the same. A bunch of XNOR gates applied to each pair of bits of A and B return whether those bits are equal or not. The AND gate returns a 1 when all its inputs are 1. So applying it to the XNOR gates returns a single bit, which is 1 if and only if A is equal to B. There are also ways to implement subtraction, division, and other comparisons, all using gate networks. For example, bit shifting the other way divides a number by 2. These are all implemented using transistors etched on a chip. Just a note, when I say the word number in this video, I am referring to an integer, or whole number. There is also a way to store fractions in a binary version of scientific notation called floating point numbers, or floats. I won't go into how they work, but the general principle outlined here still applies. To summarize, A sequence of binary on-off electrical signals is used by computers to represent a number in base 2, as opposed to base 10, which is used by people day to day. Networks of logic gates can be used to add, subtract, and compare binary numbers, and with a few extra steps, multiply and divide them too.